In this lesson, we're going to be looking at transformations of functions. Now, there are two different sides of that coin that we have to consider. One of them, which is the simpler one, which is not really our focus today, but I'm going to review it, is how do we start with a defined function and figure out those transformations? And that's entirely review, so we're not going to spend much time on it. Um, so we are going to be working with a function notation that I've shown you here, which is using the parameters a, k, p, and q to represent our different transformations. You may have also seen this as y equals a, b, c, and d. Regardless of which one you prefer, you need to be able to work with either of them. The letters that we use here are really irrelevant. The y and the x are the coordinates, the x and y coordinates. F is the name of the function. All of these other things, they're just placeholders for presumably numbers that we're going to have there. For consistency, I would strongly recommend, however, that you use whatever we're using in the context of the course, whatever teacher you have, professor you have, the textbook that you're using. Just try for consistency, but be willing to adapt yourself. So if we are given the equation, then we need to be able to, first of all, we need to be able to algebraically manipulate the equation or the function into this form. And then we start to pick out what the different things mean. So the a value, the value in front, the multiplying value in front of the function or outside of the function, that tells us our vertical scaling. And the sign of that value, positive or negative, is going to tell us whether or not we have a vertical reflection. So it'll be a scaling value for any value of a, or actually more appropriately here, we should actually say for any value, absolute value a, not equal to 1. And then a vertical reflection anytime that's a negative value. And the same thing would apply here. Our k value, which is the multiplying constant, but it is inside the function bracket, that tells us our horizontal scaling. And hopefully you remember your scaling, which is that your horizontal scaling, if you have a value here of k, that actually is a scaling by 1 over k. So for example, if I have a k value of 3, then that means I'm actually going to have a compression. So that's a scaling by 1/3. The sign of k is going to tell us whether we have a reflection horizontally. In some functions, a vertical and horizontal reflection mean the same thing, but in many functions, a vertical and horizontal reflection are different. So it's important to be comfortable with both of these values. The letter P here, which is once again inside the function bracket, P represents the phase shift. That's why we give it the letter P, and that's just a fancy way of saying a horizontal translation. That's a shift to the left or to the right. And then Q, the letter Q, I don't think has any meaning here other than the fact that it follows P alphabetically. So Q is our vertical shift, up or down. Sorry, there we go. Sorry, shifting the pages there, just got a little hung up on the processor. Okay, now another way to do this. Now you can try applying these things if you want to. Here are our 4 transformations. There's our vertical reflection and vertical scaling, our horizontal reflection and horizontal scaling, our horizontal shift, and our vertical shift. But you can actually, if you know some points on your parent function, you can also perform a transformation using this notation, which is actually quite handy. So any x coordinate, any point xy is going to change into some new point xy. So what happens? Well, we take the x coordinate, and the x coordinate is going to be affected by the things that shift things horizontally or change things horizontally. That's the k value and the p value. So this affects the x, this affects the x, this affects the y, this affects the y. And so, as a result, we take our x value, divide it by k, that's our horizontal scaling, and that actually would also account for a reflection, because if k is a negative number, we're taking x divided by a negative number, so that'll change the sign. And then we add our p value here. So those are the changes to the x-coordinate, and similarly we have our changes to the y-coordinate. So if you have a bunch of points from a starting function or a parent function, you can use this notation to very quickly and easily come up with my new set of points. Now, where we start to run into difficulties is what I wanted to focus on in this lesson, or at least bring your attention to in this lesson. The harder skill here, and something you're probably going to have to spend more time practicing, is going the reverse direction. So what if I know the before and after? So let's say I've got my starting graph and I've got my transformed graph. How can I come up with my equation? How can I come up with those values of A, K, P, and Q? And that's kind of what we're going to focus more on today. You still need to do the equation to a graph, but what about going from the graph to an equation? And in particular, from a pair of graphs and explaining the transformations that got you there. So I'm just going to go through some tips for some of the various parent functions that you might run into. Sometimes you're going to be given functions that don't necessarily have a parent function that I've talked about here, or maybe it's not even a well-defined parent function, but you still have to identify the transformations just using points. But some of these things will help you, and it's better to start with things that you're familiar with anyway. So I think the first non-trivial function that you're going to be familiar with is going to be a parabola. That generic function notation gets reduced to this form with a parabola. Notice that the k value is gone. And the reason for that I've illustrated down here in this box, which is, let's imagine I have a parabola which has 3x all squared. So there's no p value, no q value. But if I expand that bracket, 3x times 3x is actually 9x squared. So here, because this 3 is inside the bracket, because this 3 is being squared, this would be a k equal 3. If I expand this, I get an equivalent expression, which is 9x squared, but because this 9 is no longer being squared, it's already been squared through this evaluation, this becomes an a value. So a k and an a value are actually, they can be made into equivalent numbers. They're obviously not the same number, 3 and 9, but with some algebraic manipulation, I can come up with equivalent expressions for them. So in general, with quadratics, we only work with a. There may be times where you do work with k. It's depending on whether or not you've got perfect squares or square roots, that sort of thing. But in general, you want to work with a, p, and q. We generally ignore that horizontal scaling. And also, because parabolas are they're symmetric about their axis of symmetry, that's another good reason to just set k equal to 1 and only work with my a value. The easiest way to work with parabolas is from the step pattern, because if you can work with the step pattern, you can figure out the a value from there based on how the step pattern has been modified from 135 to whatever the current value is. The vertex, on the other hand, defines p and q. That's dead easy. So if you can look at a graph and see where the vertex of the parabola is, you know your p value, you know your q value, and you can just state those and put them into your equation. Okay, what if we're working with radicals? Now, a radical is definitely something, it's similar to a parabola, but it's a much more complicated function to work with, and it's a little bit newer to us as students. So the parent function, just like a parabola, starts at the origin, 0, 0. So if you can identify where that 0, 0 has been transformed to through shifts, that's going to give you your p and q values. Simple as that. Now, the a and k values, because it's actually a similar reasoning to what I showed you with regards to the parabola, in the sense that there's a square root operation here. So this square root of k, technically that's just a number, so that can come out here. But the reason why we need to keep the a and k separate is because the signs are important. If we think about the parent function of the radical, a vertical reflection of that is going to look like this, A horizontal reflection of that is going to look like this. As you can see, the vertical and horizontal reflections are different. And then you could actually also have a vertical and a horizontal reflection, and it would look like that. So for that reason, the sign of A and K are both important. So we need to keep track of both your A and K values. Now it turns out that means I only care about the sign. I don't actually care about the magnitude. I'm still allowed, if I want to, I can combine the two magnitudes into a single value. And in general, the way to get nicer values, we're always looking for integers or nice fractions, that sort of thing. The easiest way to do that is to set your A value to be plus or minus 1, and then just focus on coming up with your K value, which should be an integer value or a fraction, provided things work out nicely with your numbers. All right, so see I say that here. We want to use K for our scaling. The horizontal scaling is more likely to give a nice value. So we set A equal to -1 or +1, depending on whether we have a vertical reflection, and then we figure out what our K value should be from there. P and Q, again, those are easy. Where has 0, 0, which is right here, where has that been shifted to? So if you've got a radical function that looks like this, well, you know you've had a shift here of P, and you've had a shift here of Q. Okay, rationals. So the rational function, parent function, looks something like that. That's the parent function is 1 over x. So for the rational function, we've got asymptotes. We've got a vertical asymptote and we've got a horizontal asymptote. In the case of a rational function, a vertical reflection and a horizontal reflection are the same thing. They actually look the exact same. So for that reason, and it turns out the scaling can also transfer between vertical and horizontal quite easily. So we only use either A or K. Your choice. It's entirely up to you. And you can see I've illustrated that with a little example here, which is here I've chosen a K value of 3 because this is 3 multiplied by this bracket, and it's 1 over that whole thing. That means the 3 is part of where the x would be. Whereas in this case, I have 1 over my variable component. That's where the x would normally be. And you can see that in this case, the 1 over 3 is actually outside. So normally it's 1 over x. So this is 1 over something. This is 1 over something. And so hopefully you can see that in this case the 1/3 is not part of the what's known as the argument of the function. It's actually a multiplier that occurs afterwards, whereas here the 3 is part of the argument of the function. And I know it seems, you might say, well, these are equivalent expressions. Yes, they are. But when you represent these using function notation or in terms of transformations, in this case, this would be a K parameter, whereas in this case, we have an A parameter. And as I say here, usually it's going to be easier to work with A, so we go ahead and set K equal to 1. Okay, now that's it. You can see that's a pretty short lesson because, to be honest with you, the best way to approach this is to take lots of time, work through these exercises, and we'll work through them together. Okay, that's it for today's lesson.